Assalamualaikum, my name is Ainana Jo binti Morni. Today, I will present about our project, Automated High-Rise Water Level Control System. In high-rise buildings, high water usage can lower the rooftop tank level, causing weak water pressure on the upper floors. Manual pump operation may also cause delays, unstable water levels, human error, and even pump damage due to dry running. To solve these problems, our system automatically monitors the water level and controls the inlet flow to maintain a stable water level. Our objective is to design and simulate an automated water level control system using industrial process controls concepts. The system is a closed-loop control system with a fixed set point of 2.0 meters. We focus on the controller, a control valve, tank process, and level transmitter. This project covers only modeling and simulation, not hardware installation. The system works in three simple steps: monitor, decide, and act. First, the level sensor measures the water level. Next, the controller compares it with the 2.0 meter set point. Finally, the control valve adjusts the water inflow to maintain the correct level. This ensures stable water pressure, reduce overflow risk, and minimize manual work. Finally, the control loop compares the set point with the measured water level to produce an error signal. The controller uses this error to adjust the inlet valve until the water level reaches the desired value. This continuous feedback helps maintain a stable water level.
Next, I will explain the mathematical model of the water level control system. Several observations were made to simplify the model. The tank has constant cross-section area, the water is incompressible, and the system operates around a steady state condition. Pipe loose, leaking, and turbulence are neglected. Based on the mass balance principle, the change in the water level depends on the difference between the inlet and outlet flow rate. The outlet flow is proportional to the water level. From this equation, the tank and control valve are represented using the first order transfer function. The control valve and tank process are connected in series. Therefore, the transfer functions are multiplied to obtain the reduced open-loop plant model. Using the selected parameters, the valve gain in 0.05 and the hydraulic resistance is 40. The capacitance is 10 and the valve time constant in 5 seconds. The tank time constant in 400 seconds. So the result transfer function has two poles at negative 0.2 and negative 0.0025. Both poles are in the left half plane and in indicating the open loop system is stable. The MATLAB results show that the open loop system is stable but responds very slowly. For unit step input, the liquid level gradually reaches approximately 2 meters with zero overshoot. However, the setting time is about 1570 seconds because of the last time constant. For the sustainable input, the magnitude ratio is 0.48545 and the phase angle is negative 78.83 degrees. This shows the system reduced the input amplitude and produced a significant response delay. And the system stability was evaluated using the root locus and Nyquist method. The root locus branch begin at the two open loop poles and remain in the left half plane for positive gain. This confirms stable behavior. For the Nyquist analysis, the plot starts at +2 and does not include the critical point at -1. Since there are no right half plane force and no encirclement, the closed loop system is also stable. So the system is stable, but a controller is required to improve its response speed.
Hi, my name is Vanessa Dudok Sampai and I will present about the closed loop implementation in Simulink. The step block generates the 2 meter set point, which is compare the measured water level in the sum block to produce the error. The error is processed by the PID controller, which adjusts the inlet control valve. The valve and tank dynamics are represented by the transfer function blocks. The level transmitter measured water levels and send feedback to the controller, forming a closed loop system. Finally, the scope displays both the set point and the actual water level, so we can evaluate the system's performance. By turning KP, KI, and KD, we achieve a faster, more stable, and accurate response. We evaluated 3 controllers, which is P, PD, and PID. First, we tuned the P controller by changing the KP value to improve the response speed and observe the steady state error. Next, we added the derivative, which is KD terms, to form the PD controller, which helps reduce overshoot and improve system stability. Finally, we added the integral, which is KI terms, to create the PID controller, which eliminates the steady state error and improve overall performance. To compare the controllers, we use 5 performance metrics, which is rest time for speed, settling time for recovery, overshot for safety, final level for tracking, and steady state error for accuracy. Based on this result, we selected the controller that provide the best balance for fast response, low overshot, zero steady state error, and good stability. Now I will present about the performance of the P controller. We tested several KP values from 5 to 25. As the KP value is increased, the system responded faster, but the overshot also increased. After comparing the result, we selected KP equal to 20 because it provided the best balance between speed and stability. With KP equal to 20, the system achieved a 15-second rise time, 4.32% overshot, a final level of 1.951 meters, and a steady state error of 0.049 meter. Although the P controller gives a fast and stable response, it cannot completely eliminate the steady state error. Therefore, we added a derivative and integral terms to further improve the system performance. That's all from me, and I will pass it to Wan Alris.
We compared P, PD, and PID controllers against a 2 meter set point. The P controller responds quickly but has steady state error. Adding derivative action in the PD controller removes overshoot, but it still settles below the target at 1.9512 meters. Only the PID controller with gains KP20, KI 0.05, and KD84 eliminates steady state error and reaches 2 meters with a small 0.91% overshoot. Therefore, the PID controller is our best final choice. In verifying the stability of our selected PID controller, we performed a closed-loop Routh-Hurwitz analysis. By substituting the tune gains into the transfer function, we obtained the characteristic equation, which is 2000s to the power of 3 plus 573 to the power of 2 plus 41s plus 0.1 equals to 0. From the Routh array, all the values in the first column are positive, resulting in zero sign changes. This confirms that there are no unstable poles, proving that the system is asymptotically stable. In conclusion, all project objectives were successfully achieved. Although the open-loop system is stable, its 400-second time constant makes it too slow for practical use. While P and PD controllers improve performance, they could not eliminate steady-state error. The PID controller proved to be the best solution, achieving the 2-meter set point with zero steady-state error. A settling time of 38.75 seconds, only 0.1% overshoot, and guaranteed stability. This ensures a reliable and efficient water supply system while preventing pump dry runs and reducing manual errors. That's all from me. Thank you.
My name is Marion Andrew and I will be presenting the final part of our project. which include the stability analysis, project conclusion, and future recommendation. Stability analysis and performance verification. To verify reliability of our control system, we use three stability analysis methods. Firstly, root locus, second, Nyquist criteria, and the root Hurwitz criteria. The open loop pools are located at S equal to negative 0.2 and S equal to negative 0.0025. Since both poles lie in the left half of the S-plane, the system is stable, although the response is notoriously slow. The root locus show that the closed loop pools remain in the left half plane as the controller gain increase, indicating stable operation. This is supported by the Nyquist plot, which does not encircle the critical point, negative 1 and 0, confirming closed loop stability. Finally, using the root Hurwitz criteria with our turn PID parameter of Kp equal to 20, Ki equal to 0.05 and Kd equal to 84. All the first column value are positive, confirming that the PID controller system is asymptotically stable. In conclusion, the open loop system was stable but too slow for practical use. The P controller improved the response speed but still produced a steady state error. The PD controller eliminated overshoot and reduced the settling time, but the steady state error remained. The PID controller provide the best overall performance by achieving a fast response and zero steady state error and stable operation. For future work, we recommend implementing anti-wind up protection, adding dry run protection for the pump, improving the model using feed-forward control, and performing hardware in the loop HIL testing before real industrial implementation. That concludes my presentation. Thank you for your attention.